Okay, so I guess we can start. Chose to make a little difference this week, since we need to cover some more material before the deadline of assignment 1. Probably better to have it on Tuesday rather than Thursday, which is closer to the deadline. So I will have 1 hour lecture today, finishing up this topic about lighting and colors. And then we will have a 1 hour lab session afterwards where we will introduce a new lab on lighting, or people can work with assignment 1 if they want to. So this lighting lab is not connected to the first assignment. That will be sort of like towards the second one. On Thursday I was a bit uncertain whether we were gonna... We're definitely gonna have a lab session then as well, although we're in an auditorium. It's not the most ideal thing, but I think we'll find a way to work around that. And also thought that I might introduce assignment 2, but perhaps that's not a good idea since it's very close to the deadline of assignment 1. So we may just have continuation of this lighting lab on Thursday and assignment 1. And then I will have a little session on exam dates, because during the last lecture, I basically talked a little bit about this. I said I was going to put up a doodle poll on possible exam dates, but I discovered that the 2 alternatives I had put up was basically on holidays. Sort of official holidays, like the 1st of May and the 17th of May. Now the 17th of May I think is not a day where we can have an exam. So that option sort of fell out. I'm also uncertain about teaching staff being present on the 1st of May to start the assignment, so we may have to pick some other alternatives. That's why I didn't put out the doodle poll a couple of weeks ago. So I will have a little discussion about this on Thursday, but for now, just to mention what this was all about. So the exam is a 72-hour session, basically. And this means that you will have 3 whole days to work on exam. That's what it says. Now, the exam office has put up these days here, 18th through the 20th of May. These are of course 72 hours, but unless we're going to introduce this at 12 o'clock in the evening on the 17th of May, it gets a bit less time. So I'm thinking about extending that one into the 21st, which is also a holiday. Having a deadline on a holiday I think is quite okay. Compared to having teaching staff on that day, although I wouldn't mind. I'm not sure if I can do that. But I will ask about this. So then we have basically 2 alternatives to the dates that are set on the web page already, basically decided. It's to have it the 2nd weekend of May, so then you'll get to know the task on the 8th of May, and you can work on this until Monday around 12 o'clock or something. The other alternative is to have it from the 22nd of May on to the 25th. So I don't know if anybody here is busy on any of these alternatives, because then we can just rule it out at once. Anybody has some other exam or something that doesn't suit any of these alternatives? No problem? So the point is basically to do like previous years, to have the exam during the weekend. But if it's fine for you, we can just also have it on the days that are already set, and then just extend it into this holiday on the 21st. That's really the same for us. So anyway, just think a little bit about this, and I will go back on this on Thursday at the beginning of the session, basically. And I'll put up a doodle poll so that people can vote. And it was very important that everybody agrees on one date, because we don't really have the possibility to operate with several exams. So maybe we'll end up on the dates that are already set, because those have been known online for a while anyway. So have a look at this, have a look at your schedule, and we can come back to this and then try to set this up on Thursday. Okay, just to remind you, the deadline of assignment 1 is 1 week from now, plus some hours. So it's at midnight on the 23rd. Assignment 2 will be launched, I think next Thursday. I'll start to talk about that. So you have about 2 months to work on it. So it should be delivered the 24th of April. So it will be a bit less than 2 months. And also, you delivered on the 3rd. I thought that we use 1 hour on the next lab session on March the 10th to present your solutions, because you're going to give a presentation of what you did on assignment 1. So people are okay with presenting this on the 10th of March? Then you have 1 week after the deadline to it's just a short description of what you've done, like 10-15 minutes or something like that, so it's not a big deal. But it's just so you can explain to us and everybody what you did and how you choose to do it, basically. So 10th of March, unless anybody objects to that one. Okay, so that was that. I will continue where I left off on Thursday, 1.5 weeks ago, to wrap up on lighting and colors. Now we basically talked about some physics behind lighting and colors, and also some methods we could use to get a physically accurate rendering. I'll repeat a few things of that, but the main topic today is to basically talk about how you can program these things, so that you can be able to do these labs. So, as I mentioned a couple of weeks ago, there are 3 main factors that defines the perceived color. It's the illumination, or the light source, which may be the sun or some, light like this or whatever. It may also be light that has been bouncing off several surfaces several times, so you get this sort of ambient light, which you call it. But anyway, you have an illumination that covers a certain spectrum, a certain part of the visual frequency spectrum. The sun is completely white, or almost completely white. Other light sources does not have that sort of a ideal spectrum, so it will make the color appear a bit different. You have the object, which is basically described by its physical properties, the way it absorbs or reflects electromagnetic radiation, or photons if you like. So that's basically what's given by an object. Then of course you have our eyes or the camera, which is either a sensor or your retinas with light sensitive neurons that basically converts these electromagnetic waves into signals and then represents them in your brain as a color of some sort, basically. So we will not really deal with the perception, but we will deal with this modeling out here, from light source to the reflective properties until what reaches the eye, basically. So that's what we will be dealing with. Okay, I also mentioned a little bit about our vision. I talked about 2 types of neurons that is situated on the retina. One is the rods, which is the one that is basically in black and white or in a sort of bluish color that you use to differentiate between very low luminance levels. So night vision, for example, is connected to those rods. And then you have the ones which is most dominant in broad daylight, the cones, which is this gray curve here. There are 3 of them, RGB, but if you put all their responses together, you get the gray curve. And those make you see colors in broad daylight, basically. Now, why did I put up this one? Well, last time I just talked about the response of the three cones. We will concentrate most on what you see in broad daylight, not so much in night vision. So it's called photopic vision, and if you put them all together, you will see this curve, which shows you the sensitivity for different colors in the spectrum. And if your luminance value, the light intensity, should be 1, then you see that 72% of the green component is in that. And then about 21% is the red component, and only 7% is the blue. So you have a much higher sensitivity for colors that are green yellowish than you have, for example, for red, and definitely for blue. So most of the lightness lies in that area. That is an important thing to think about when it comes to representing something, because distortions in this green-yellow area will be much more visible than, for example, in the blue or the red. So that's basically it. Any questions to that? Okay. Just continue. All right. So a little bit of summary about the last lecture. Basically, you have the light that you perceive, or the camera perceives, comes from the light that may be emitted off the surface itself, or ambient light, which is coming from reflections from different surfaces in the room that is directionless. And it's also light coming from a directional light source. In this case, we showed a point light source. And how strong that appears will depend on how that light hits the surface compared to its surface normal. And the other factor that comes into account is in which direction the camera points. So all these things will determine what color you perceive, and also, of course, also what the surface is absorbing and reflecting matters. And what you perceive over here, the intensity and the color, will depend on all these things. And all of this could be physically accurately summarized by this rather heavy equation here. So the light output, which is the leftmost component here, which you will perceive in the direction here of W, is basically a function of anything. It is this term. Anybody remember what that was? It doesn't come from any. You see the vectors.
Material properties.
Well, the material properties are also determining how light bounces off. But you can see that omega prime, which is the incoming light direction, is only in this integral. But you have this extra term that is independent of that. So it can be two things. It can either be that the surface itself emits light, like it's glowing, for example, or it can be ambient light that is sort of like light scattered off from the environment, and that is just there without any particular direction. And then you have all the directional light that comes in, that can come in from any angle for a given point. And that is basically summed over a sphere, because that's a nice and symmetric surface to integrate over, to sort of incorporate all direction that comes into a point. So you integrate over the spherical shell. And the surface here has a property, which is this FR, which is the reflective properties of the material, what will bounce back. You could also have a function here that tells you what is absorbed and transmitted and so on and so forth. Then you use another function for that. But the material properties, and then you have the light itself, the light source, which is basically dependent on its position. Of course, the angle of incidence with the normal of the surface, shown in green there. And of course, that also depends on the frequency spectrum it covers. Which color does the light itself have? And this last term, which is basically the angle of incidence, the angle at which this light vector comes in compared to the normal. And this inner product, basically, if I put it smaller here. So the strength of the directional light depends on the cosine on the angle of incidence. So your light coming in here, this is the normal of the surface, and it's given by this one. Now, as I mentioned in the last lecture, it's very important to normalize these two so that they have length equal to 1, because if you do that, you can exchange this inner product with cosine theta, or in this case minus cosine theta, because the vectors are pointing in different directions. Okay, so that was that. But don't worry, you don't need to. If you look at this equation, there's a big problem with it. which we mentioned, which was, yeah.
Integrations as the sum of like an infinite amount of points in that area. We can't physically do that.
It is very, very hard to compute, yes. So you will not be able to do this in a, you have methods that will replicate this equation, try to make it come close to this, which is also computationally feasible. Yeah, because you have to do this, as I say, for every point on the surface, which is quite demanding. But this is sort of like the physical description of this process. This is a physically accurate description of how light will be perceived during this process. But we talked about several ways on how you could replicate it. One was ray tracing, another was photon mapping, and one was path tracing. I think path tracing or photon mapping is sort of like the gold standard you use to compare rendering to. They are quite physically accurate, but they're quite heavy to compute. But none of them are very good for real-time rendering, which we will be considering. So we will look at an even more simplified model than that. But you could use this photon mapping, for example, as a means of comparing a method, how good it is. So we will look at a very simplified model that looks okay, perceptually okay, but it's not a very physically accurate one. So you could use this in any case. You don't really need to describe a phenomenon very accurately. So we wouldn't use it for a physics study, for example, but to make animations and games and these sort of things, this should do basically. So it's a simple approximation to the render equation, which is not physically accurate, and it's called the Phong model. Does anybody remember the components of this one? There's three main components written here. So first and foremost, you had ambient light. Anybody remembers what that was?
No, it's just to differentiate the object in the space, kind of the color it has. It's not really coming from a lighting source or something.
Well, it's almost right. It is coming from a lighting source, but
it's like
yeah.
I guess the sky would cause ambient light because it's blue, and then it would be the color of the shadow, I guess.
Well, you could. If you could take the sun away, in a sense, you will get ambient light in that sense, because it would just be light scattered off something, right? So it's onto something. Yeah. But you won't have shadows because that's directional light. So ambient is directionless, but it is light that is scattered off many environmental things, so that it becomes completely directionless. So you just add the luminance value to the whole structure. No matter where you put it in space, it will look the same. It won't change because there is some light that is getting stronger or weaker. So basically, directionless light. The diffuse, anybody? Yeah?
That's like coming from the main source of light that we have and has a direction, so it's in one direction of the other.
Yes? So it is dependent on the incoming light direction, but it scatters off the surface in all directions. So the outgoing light is not directional dependent in that sense. So many of the surfaces in this room are diffuse. For example, when lights hit it, it depends, of course, on the angle it hits, but what is reflected back goes in all directions. So if you move around the object, you will basically see the same color from the same points on the surface, whether you move around or not. And last was specular. Yeah?
It's how much the surface reflects light, or how much is it like a mirror or something?
It is something in that direction.
It reflects the light.
It reflects. So, but mirror is one extreme.
Yeah.
You can have many ones in between.
Yeah, you have like a whole range.
Yes.
How much object maybe?
So in physical terms, you have diffuse. It will depend on the incoming direction, right? But it will spread out in all directions from this point. But the specular
Look like
will be reflected, but it will be reflected in a much narrower area, right? So something like that. So it is also dependent on the direction of the camera or the viewer. So if you put your camera in front of here, or your eyes is looking at this point, you will see it. If you're looking from this angle, you won't see anything. And it's if you think about walking along the ocean on a sunny day, or outside in when there's snow, right? You will see these sparkles. And you can move a little bit before the sparkle disappears completely, so you have a little bit of the movement, but once you move enough, that speckle is gone, another one will show up, basically. Yeah, so that's the Phong model. It's those three components. If you add them together, you call something get something called Phong reflection, and it looks quite perceptually nice. And this will do for us in this course. So we will basically work on this one. But two other aspects we have to include. One is attenuation. Oops, that was not spelled the right way anyway. So attenuation, if you, for example, going to describe light sources, you will need to take in attenuation to make it look natural. And sometimes you also have to think about something called a gamma correction. I will talk about this, all of them at once. Yeah, just before I move on, OpenGL Lite was something that it still exists, but it's deprecated basically. So it's old and outdated. They don't deal with this anymore. So now we basically code this from scratch. It gives you more flexibility. So just to say, if you see any tutorials with this sort of GL lighting, then just skip it because it won't do you any good. Okay. Let's see. All right. Okay, so I'll just talk a little bit more detail about each of these three Phong components. First and foremost, the ambient light, directionless. All you need to do to get that lighting type is basically to add whatever surface color you have. So take this red ball in the image here. It's just having a red value, so the other two components are 0. And then you just have the ambient intensity, which is just multiplying with a given factor, here 0.5. It could be anything between 0 and 1 in a sense. And then of course what you get out is a damped version of this one. So it's very simple. You just have your surface color and you multiply it by the factor which corresponds to the ambient light. Diffuse depends on incoming direction, but it's scattered in all directions out again. You can see how that's done here on the right. So every surface has a little bit of granularity, right? And it's not completely smooth in many cases. And then, of course, light bounces off in different directions, and you get this impression that it's basically spread in all directions like this. It's shown there in the ideal case. Yeah, here I show the computation in world space. You can compute the light in many spaces, but usually do it in world space, or you could do it in camera space. So you remember what that meant? World space, camera space.
Is it on the U material, the projection?
Yeah.
All it is a projection view, and can I remember the third one? Something makes the world view.
The last one was the model matrix.
Model matrix. Yeah.
Yeah.
Doing it on the camera view would mean that we do it afterwards. We have projected everything onto a previous screen.
Well, when you project it, you call it clip space. Camera space is before you project. So you have your yeah.
The world space is the world around you.
Yeah.
And the camera space is basically changes the basis of the coordinate system.
Mm-hmm. Depending on where you're looking.
Yeah.
So just to repeat this thing. You have your model space. Or I can actually take up the drawing. I think that's more clear than. Let me see. So we have this one, if you remember back when we talked about transformation. You have your model space, in which is the space you model, whatever you want to model in. This is where we made the triangles. Then you map this into a world space, which is where the object interacts with other objects and so on and so forth. That's where everything is going on. And then you have the camera space, which is basically the direction you point the camera in the scene. And in OpenGL, then often we can basically keep the camera fixed and move the roll around, of course, and that's what you often do. And going from here to here, you had 3 operations. Usually, remember what that was? Yeah?
Translation, rotation, and scale.
Exactly. So we call it the TRS rule. So first you scale, then you rotate, then you translate. That's how you got from model space to roll space. I repeat this now because when you do lighting computations, you usually do that either in roll space or in the camera space. And then you have to transform your vectors to so that you're sure that they are all in the same space. For example, you have to transmit your vertices to whatever space you do it in, and you have to, of course, also transmit your light vectors there, depending on what they are. So back to what I was talking about. So that's why I say if you compute in world space and you have a light position in space somewhere, then you have to transform your vertex position using the model matrix, which was this translation, rotation, scaling thing. If you want to do this in camera space, you will also have to use this. Anybody remember what it was named?
Can you repeat?
If here I talk about doing the lighting computation in world space, then I basically just have to transform my vertices using this. If I wanted to do this in camera space, which is also possible, then I would have to multiply it with also. Remember the name of it? There's many names: camera matrix, viewing matrix, look at matrix, exactly. So then you just have to take that another multiplication. But just be sure when you can compute a light that you have all transformed to the same space. And usually it's most convenient to do it in world space, but you can also do it in camera space. I think the lab is done in camera space for some reason. Anyway, so how do you compute this diffuse light, given that you are in world space? Well, you have a light position in world space somewhere, and then you have your transformed vertices at some other point in space. So let's say we are in space now. X, Y. Oops, that was not nice at all. You're in there, you have a light source, you have a point, whatever that is, and the light direction is basically the difference between the light position and the point transformed into world space. So TRS times vertex position. Now you have transformed not only your vertex but also your vertex normals to world space. So now everything is in the same place, and you can say that, okay, this point has a normal which is given by whatever vertex normal you have set. And the vertex normals you set as another attribute. Just like you set color and texture coordinates and those sort of things. Now you set a triplet which corresponds to the normal of the vertex. So you can put it in the same VBO, you can set up another VBO, those sort of things, but you have to put up another attribute pointer again. So now you have 4 attribute pointers basically. 1 for position, the vertex, 1 for color, 1 for texture, and 1 for normals. So now you can start to compute. So you have the incoming light, or the light direction, which is the light position minus the model matrix. So you have a vector pointing in this direction, basically. And then you have your surface normal, which I can draw like that, which is depending on what normals you put in the VBO. And then, of course, you have an angle in between. So you have your light vector, your normal, and you normalize both of them. So the normalized light direction is basically the normalization of this difference. You see this?
You get the unit vector?
Yeah, to get the unit vector, yeah. So then you can very easily compute it. This one is pointing towards your light source over here, which we call L vector. You have the normal vector here, which is also normalized. And then the diffuse component is basically from this inner product we wrote. You have m dot L which is, of course, if these are equal to 1, just becomes cosine of the angle. So that's why it's a good idea to normalize, because then you can replace this inner product with just the cosine of the angle between them. And this is the angle of incidence. Right. So you compute your light direction, difference between light position in space and your vertex transformed to roll space, vertex normals, and then sorry, not that's the vertex position in space. Yeah, I said normal. It's the vertex position, and then of course you have the normal, which is also transformed from. You have your normals, which is the model matrix times the vertex normal, basically. So they also have to be transformed to the right coordinates. Is this okay? Understandable? Or completely weird? Okay, so it will help to sit down to the lab. Just remember that all the attributes that you want to compute with the row space has to be transformed to the right space. So you have to transform your positions. The difference between the light position and these transformed positions will give you the direction of light from whatever point you have. The normal vector you have set in the model space, and you have to transform these also to the row space. You do that using the same operations. And then you can compute this diffuse factor, which is basically the dot product between those two resulting vectors. And since we now have made these vectors point in the same direction, that should always be positive. Right. Unless
Can you just repeat the last part?
so when we compute the diffuse factor, we take this dot product between these two vectors, the normal of the surface and the lighting direction. But we take this max, so we will have something positive here always. So at the least it's 0. Why do we do like that?
Because it's 90 degrees at 0.
Yes, that's true. But it could also be negative, right? Which would mean, in this case, that if this is your surface here,
we don't.
exactly, you don't see it, and that's because the light is coming from behind. Right. So unless your surface is transparent, you don't really want to care about those ones. So if you have a diffuse surface, then basically whatever comes up from behind is not going to be seen anyway. Because then these vectors would point in different directions, then the light direction would be the other way around, because the light source would be down here somewhere, and the dot product would become negative. Okay? Also, one thing to note is that once you have this, you have a vector that describes the material color, RGB usually. You have light intensity, which is also an RGB vector, because in that RGB vector you could also describe the color. You may operate with two numbers here, like light intensity and light color, but it's just two numbers multiplied, so you could just operate with one vector where you have both multiply the intensity you want as well as the color at the same time. So you can pack them into one vector for light intensity. And then you just multiply it with this diffuse factor, which makes the light directional dependent. So specular, it's quite similar. The only difference is that now the viewing direction also matters, right? So you get these speckles you see on the sea surface there, for example. To model that, you will have to have just a little narrow area where you can see them. So for example, to the left here, your camera will detect it. To the right here, you won't. Or in more general, if you see this lobe of arrows coming up here, if you're looking in this direction, you won't see nothing. If you're looking straight into this, in the direction of any of those vectors, you will see something. And it will just be a limited area. And you can think about that when you walk along the sea, for example, that these sparkles, they will last for a while and then they will disappear and another one will show up and other ones will disappear and so on and so forth, but it's not exactly like a mirror. Yeah.
So most of our programming, we won't program this in the C++. Most of it will be in the shader, right?
Yes, you do this mostly in the shader. Yeah. I'll get back to that. So this is basically either done in the vertex or fragment shader.
Yeah.
So it's basically shader language.
Yeah.
Okay, right. This is almost the same as diffuse. You just have to take another thing into consideration. And so now we have the incidence vector. It's the one that comes here. So the incident vector comes in like that. Now minus that one will point towards the light source. So I'll just draw that in blue. Like that. So that's the incident. Let's call it I. Right. Then you have your normal, surface normal, which is again transformed to the right space, right? You have to I transform it to road space or a camera space depending on where you do the computation. But anyway, let's now say it's transformed to the same space as incident. So you have y vector, you have n vector, and that first operation you do is to reflect this upon the surface normal, and you will get the reflected vector r here. And we should keep them all normalized, so we could use this relation up here. We don't have to care about the length. Okay? Then you have the surface to camera, which is basically another vector. Let's call it viewing vector. So if your eye is up here, for example, or let's the same. So if you're watching this from this angle, you will have another vector that points in the direction of your eye. And that was not very accurate, but anyway. Let's call it V. Right. So it's they call it surface to camera here, so maybe we could call it S instead. Right. And now the dot product between these two. Here we'll have an angle, let's call it gamma. And that will decide the strength of your, not only the strength but also the extent of this specular light, right? So again, if all these vectors are normalized, you can say that this dot product r times s is equal to cosine of gamma. Okay. The thing is that around this reflected vector, you will have a certain area in which you can see, as I tried to draw up there, right? And depending on how they call it how shiny your object is, depends on as you mentioned, whether it's a perfect mirror in which it will reflect only in one direction, or if it's a bit more diffuse, so it will, as I show up to the right there, be reflected in more directions. And how you can basically compute this in a simple way is to just take this cosine theta here, this whole thing, to the power of this lightness, which I just call n in this. That's not very nice to. Let's call it L dot n. So some factor or some lightness factor. Very small. Anybody who can see why that would give you the wanted result? So a little hint is that cosine at 0 starts at 1, right? And then it goes down to -1, right? And it goes up to +1 again, and so on and so forth. And we don't really care about what happens beyond one period, but for this particular case. But the cosine is defined between -1 and 1. When you put that to a power of something, what you get out is 1, of course, at angle 0, right? So this is gamma here, sorry. And for all other angles in between -1 and +1, you get, yeah, and you get less than 1. And when you take a number less than 1 and put it to some exponent, it gets smaller and smaller, yeah. So the larger you put this Ln factor here, the smaller this area of outgoing rays will be. So now you have a way to control how specular your light is, basically. So if Ln is really large, you get a very sharp one. It gets more and more like a mirror. If it's close to 1, you get something quite broad. And therefore it's called shininess, because if it's acting like a mirror, it's really shiny. If it's just some specks like on the surface of water, it is shiny still, but not as shiny. But still it's a specular reflection. Is this understandable, or? So basically that's what you need to do. You need to take this incident vector, you need to reflect it upon the normal, you need to take the inner product or the scalar product between the viewing direction and the reflected vector, and then you need to take that inner product to the power of n, or to the power of the shininess factor, and then you will get this specular. And here you can experiment a bit depending on how specular the surface would be, and of course also what sort of surface you have to make it look natural. And then basically you have the same as you had with the other ones, this specular coefficient, which we call it, which is this one. You just multiply it with the material color again, RGB, as well as the light intensity, which is again RGB, and then it's scaled by this specular coefficient. And it's depending on direction through this angle here. Okay, so in lab 6 we're going to play around with this, so you get this more into your fingers. And that's why we choose to have it right now after the lecture 2. So it's sort of like a bit refreshed, and you can ask questions about this if you haven't gotten it completely. Right. So 2 more things that we have to talk about. One is attenuation. If you have a point source, the light emitted from that, or the energy emitted from that point source, will spread out on a sphere, right? And that spherical shell will get larger and larger the further you are away from the light source, right? And therefore, the energy you will observe per unit area will go down. Meaning that if your retina is further and further away from the light source, less and less energy will reach your eye, right? And this is some sort of attenuation that makes the light looks dimmer the further you move away from it. And in physics, this is known as the inverse square law. So basically, the light takes off by the square of the distance between the light source and the receiver. In this case, d is the distance between the camera and the light source. And you will get this dimming effect, as you see here. So to make a point source look natural, you have to take this into account in addition to all these phone components. Now, when you compute this, you don't use this 1 over d squared, you use this one. Guess why?
When d is 0.
Hmm?
When d is 0.
Yeah, exactly. Otherwise, things blow up and you get into trouble. So, it's to avoid that. So basically, you just have to write this into a float, and then basically take the distance between the light source and the camera to the power of 2, and you will have this effect. So now you're nearly at the final color. So you have the ambient component, which we talked about first, directionless light, and then you have the diffuse and the specular light, which I just talked about. And both of these are directional, so they have to be attenuated, because anything that spreads in different direction will attenuate as you move away from them, right? Because this half, or this structure gets bigger and bigger, and therefore at any given point here the energy gets lower and lower, right? I wonder if, should I just finish up or should we take a break?
Just finish up.
Finish? Okay. Sorry that this goes a bit over time, but let's see if I'm still streaming here. Right, the last thing has to do about perception. So our eyes are basically tuned in a way that makes us differentiate things more accurately in darker regions than in very bright regions. So we have a much higher resolution in the darker areas of luminance than towards the lighter ones. And this probably has an evolutionary explanation that it is an advantage to be able to see in dark, basically, to avoid dangers or whatever it was. So if you look at a linear scale, which is, for example, a camera sensor, it would, if you take luminance values between 0 and 1, it will look something like this great scale charge on the bottom there. Whereas our eyes will look more like the one on top. So you can see that we are seeing much more, we are much more fine-grained in darker regions of gray, whereas when we get closer to the white, we have less resolution. So the one on the bottom here, you physically say was the most natural, but our eyes are adapted to work like that. Now, in many cases, when you compress images, for example, they usually have done this gamma encoding already. And what that means is that they have, when you want to digitize an image to be able to communicate it or store it on a computer or whatever, you have to distribute bits to every pixel, right? Or every value that the pixel can take on. And a gamma corrected picture means that you have used most bits to encode less light regions, or darker regions basically, and you use less bits to encode the lighter ones because in the lighter regions you are less sensitive. So it would be a waste of bits to put in there. So often this gamma correction is already done in images to make them appear more nice to your perception. So just to wrap that up, if you take a camera and you look at, you point it at a light source that goes between 0 intensity and 100% intensity, then the camera would of course say that at 50% intensity it observes a 50% output. That's not the case with our eyes. We would say that a much darker value would be 50% output. So we would perceive this as 50%, which is much darker than that one. And the difference between them is that the camera will follow this purple line, whereas our eyes will follow this blue line there. And to make this a bit short, this curve, this blue line can basically be easily described by taking whatever intensity value you have, I, and then just take it to the power of 1 over 2 times 2. Now, I won't explain why now, but if you plot that curve against the one that is basically measured from our vision during experiments, you get just this. So the final thing you need to do if you need to gamma correct the luminance values is basically to take that color we already obtained. Oops, sorry. This one, and then just take that to the power of 1 over 2 by 2. But as I warned here, for example, when you upload some textures or something, then in many cases this gamma correction is already done, so it's basically unnecessary to do it. That's what I mean, that this doesn't always need to be done. I think, for example, in the next lab you have a texture and it's already gamma corrected, so you don't need to think about it. But you'll usually see if it's not, because then things will appear unnaturally dark, basically, and it's hard to differentiate contrasts. So it's just a last trick to make this appear perceptually nice. Okay, so just before we end up, I just would like to talk about where we do the computation of the Phong components. So you have two possible ways. You mentioned this a few minutes ago. So you have two places where you can compute this Phong model in the pipeline. One is, yes. Can you see from these images which is computed where? Yeah.
The first one is probably computed in the vertex shape.
And
The
because,
second one in the fragment.
yeah, that's exactly right. Do you see why?
Well, the fragment shader deals with a lot more points than the vertex shape.
Yes, exactly. So in this case, it is done in the vertex shader, and what you do there is that you have normals connected to each node, right? And then you compute it like at these points, and then the color in between is just the interpolation. And then, of course, every pixel in between these normals will have the same color, and you'll get this blocking artifact. In the fragment shader, you interpolate the normals of each vertex. So you get a normal field on the surface, and you use these normals to compute light at each given pixel. And that makes all the difference in the world, because this is exactly the same sphere. And here it looks, you can really see that it's not, that it's consisting of patches, right? In this case, it's harder to see, at least. And this is a trick you can basically do, which is quite convenient for you, is that doing these computations in the fragment shader will give it a better appearance. But there's of course a problem with that too. It's the world is not ideal. Can you imagine why you would have these two options?
Performance.
Exactly, yeah.
Because the vertex shader is called per vertex.
Yep.
And the fragment shader is called per color point.
Yep.
On screen.
Per pixel.
Per pixel.
So I have to mention what they say in the literature now is that, you know, computers today are so powerful that usually you can do fine with doing this in the fragment shader, but in very heavy applications you may have to do certain calculations there, but the appearance will be much worse. So that's basically these two things. Phong shading is basically computing, note that Phong shading is not the same as the Phong model, but Phong shading is computing the Phong model in the fragment shader. And it does so by interpolating surface normals between vertices instead of colors. And then it's more computationally expensive. The flat shading is basically computing the light per vertex and interpolating the colors in between. And of course, it's then easier to compute done in the vertex shading. So I'm sorry I went a bit over time. We should probably have a break. Do you want to have a 15 minutes or 10 minutes or?
10 to 15 minutes sounds fine. 10
Hmm?
to 15 minutes sounds fine.
Okay, good. So then I'll introduce the next lab in 10 to 15 minutes, which is connected to this.
Ja, dat gaat.